All right, so this right here is the enzyme ribonuclease A, and this is the first mechanism that I really want to get into. To me, this is like a very simple mechanism that shows everything that you need to know about acid-base catalysis. Now, the first thing that you do whenever you look at any sort of enzyme mechanism is you need to be able to distinguish between your substrate and your enzyme. Now, this is kind of simple because when it comes to the substrate, well, you're looking at an RNA molecule, and it's right here, RNA. Now, when it comes to the enzyme, what you always want to be looking for is what are the amino acids that are involved. Now, this semicircle that we have here in brown, that is highlighting our that is showing our basically our active site and the makeup of the active site. But what it does is it highlights two specific residues, histidine 119 and histidine number 12. What I'd like you to do when it comes to looking at those two amino acids is look at the protonation state. Now, if I didn't tell you that this was acid-base catalysis, I think that you'd be able to deduce it because of the fact that, well, histidine in your starting spot right here, I know I just drew a star by another star, but in your starting state right here is deprotonated. Histidine 119 is protonated. Then if we look at our final state right here, well, our histidine in that same position is again deprotonated, and our histidine in this position right here is protonated. Now, what you can see, and your RNA molecule is broken. So what I'd like you to do is I'd like you to see, well, we've got this N right here in our histidine ring that is deprotonated, and it's got a lone pair of electrons. What that is going to do is it's going to target that hydrogen on our 2' OH group. Now, what's going to happen with that is the electrons here are going to swing down to that phosphorus, in which case we're going to make a cyclic 2,3 nucleotide. That will effectively break our bond between our RNA and our RNA molecule, because what that's going to set into motion is these electrons right here to swing down to try to pick up that hydrogen and deprotonate that histidine 119. So effectively, in our very first step, we've got 1, 2, and 3. Those 3 simple movements are going to break our RNA molecule. Now, what we have to do is basically return our enzyme to its original state, and we have to more or less put the finishing touches on our RNA molecule that we've broken. One of the things that we need to do is we need to break this cyclic nucleotide, or we need to return it to an acyclic nucleotide. And so what we're going to do is we're going to bring in H2O. Now that H2O is going to act as an acid because this newly deprotonated histidine 119, it's got a lone pair of electrons that are going to pick up that hydrogen from that water molecule. The remaining electrons between our hydrogen and oxygen are going to swing up here so that they can bind to that phosphorus or make a bond with that phosphorus. The bond between this phosphorus and this oxygen, well, what that is going to do is it's going to pick up that hydrogen or that proton, so that we can then have the deprotonated nitrogen in that histidine number 12 residue. So what we have is histidine 119 and histidine 12 acting in different functions. One acts as a base, one acts as an acid. And we have this exchange of, we have this movement from a protonated state to a deprotonated state. Now, with all of that said, one of the things that's very important to recognize about this is there ever a bond formed between our enzyme, so either of our amino acid residues, and our substrate? No, there's not. There's movement of electrons, there's an exchange of protons, but there is no bond formed between our substrate and our enzyme, which is a good indication that this is not covalent catalysis. There are some amino acid residues that you should think about as kind of being hallmarks of acid-base catalysis. And generally you should think about which groups can be ionized, and that's going to be a good place to start. That's not always the case, as we will see in just a moment. So there's only acid-base catalysis taking place in the RNA state. The next enzyme that I want to talk about is lysozyme. Now, lysozyme is going to hydrolyze the peptidoglycan layer of bacterial cell walls by breaking the beta-1,4 glycosidic linkages between NAM and NAG, or N-acetylbutyrate and N-acetylglucosamine. So NAG, NAM, NAG, NAM, NAG, NAM. So those are repeating elements over and over again. What lysozyme is going to do is it's going to cleave this glycosidic linkage. This is a beta 1,4 linkage. Remember, it's in the beta position. It's pointed upward in the same direction as carbon number 6 here. And what we're going to do is disrupt that bond between those two, between those two sugars. This is specifically breaking between NAM and NAG. It is not going to break this bond right here. Okay, so I'm going to put an X. It will not break that bond right there. So effectively, what it's going to leave behind is a hydroxide group right there, and a hydroxide group pointing downward. So this oxygen is going to go with the NAG. Now what this right here on the right hand side is showing is it's showing the input and output of I cannot remember the name of it. Well, an isotope of oxygen. So you can see the label that the oxygen from the H2O that was used in this mechanism goes with the NAM rather than the NAG. Okay. So one of the important things about this particular enzyme is to understand not only the amino acids that are involved in the active site, which are shown right here, because this is where lysozyme cuts, but also all of the different kind of coordinated efforts of all of the other amino acids. So we've got aspartic acid way up here. Now, is that aspartic acid going to be involved in breaking any sort of bonds? No, it's not. All that it's doing is it's forming hydrogen bonds with a hydrogen here and a hydrogen there. So that carbonyl oxygen is going to help stabilize that. So in order to help that make a little bit more sense and to give some insight into the processing of this molecule, all of these different sugars are labeled A, B, C, D, E, and F. So that can show approximately where lysozyme is actually going to cut, because lysozyme is going to cut between NAM and NAG, N-acetyl and N-acetyl N-acetylglucosamine, but it's going to cut between sugars D and E. Now, all of these different enzymes all of these different amino acids are involved in the proper positioning of this particular substrate. So the cool thing about this is if we were to take this tryptophan right here as an example, and we were to mutate it to a glycine or something, and if we were to take this tryptophan right here and mutate it to an alanine, the question is, could lysozyme still cut this? Yeah, it probably could. But is it going to cut it as well or maybe as fast? No, it's not. Because you've done something to disrupt not the active site, but you've done something to disrupt amino acids adjacent to that active site. So this gives a good display of all of the different amino acids that are involved in this catalysis.